Okay, so I'll start by introducing myself. I'm Omer Anson. I am the Dragonflow PTL. I've been working on Dragonflow for about a year. Dragonflow itself, it's well, given a cloud where you are running a bunch of VMs, then you want to have these VMs be able to talk to each other using the network. Now, somehow you need to tell each VM to which network is connected and to move the packets along. This is what Dragonflow does. Dragonflow is a part of the OpenStack project. It's fully open source, fully vendor neutral, and basically it allows virtual machines in the cloud to talk to each other. It uses inside Redis because somehow you have a policy. You have to maintain what virtual machines you have, what ports they have, what networks they belong to, what are the IPs, security considerations and such. Somewhere you need to store this information. We use a distributed key value store for this, and Redis is one of the main solutions we use for this. Additionally, we need, whenever there's a change, we need to somehow propagate this change throughout the system. Again, we use Redis as a publish subscribe mechanism so that events can be passed along. So more deeply, what's Dragonflow? As I said, it's a fully distributed cloud network implementation. Given a cloud network, given a cloud with virtual machines which are connected to the network, we need to move the packets along from one virtual machine to another according to what is allowed or what is forbidden. And Dragonflow, as I said, is part of the OpenStack project. We use OpenStack as the API to define this network, to define the cloud. And Dragonflow is just the implementation, just the actual part of moving the packets along. So how many people here know about OpenStack? Or? Okay, so OpenStack is a modular architecture with core services. Mostly it provides a set of APIs, and on top of these APIs, a set of implementations. So you have an API for compute, which allows you to define virtual machines, for networking, which allows you to define the network between these machines, storage for block storage or image storage, an identity service, which allows you to define authentication, a dashboard to able to connect visually to all these APIs. Specifically, we work with Neutron, which is used to define the networking between virtual machines. So more in depth into what Dragonflow does, we're given that we have a Neutron server where the virtual networks are actually defined. With API commands, we know how to set up the networking. These API commands translate into information that we write into the database. This is the Redis block down in the middle. And this information is then propagated into the compute nodes. The compute nodes are the actual hosts that run the virtual machines and where the actual work has to be done, where the actual packets have to be moved around. So where does Redis come into this? Redis, as I said, is the database in the middle. It both stores the policy of what virtual machines exist, to which networks they connect, and the such. And it is also used to pass events of modifications to the compute nodes when such modifications happen. Now, in this presentation, I want to present Redis as a use case in Dragonflow. So we ran some benchmarks to see how well Dragonflow works in general and how well we work with Redis specifically. Our test is for control plane. We send an event using the Neutron server. We send an API event, and then we see how long it takes all the hosts to receive this event and act upon them. So in our environment, we have 39 physical servers. They were given to us as a courtesy of Strato. We took 6 of these servers and created a Redis cluster with 3 active members and 3 slaves. So we have one slave per active member. And then we started the first test. The first test includes only Redis. We took our driver so that any slowdown is our fault. what we have is a single event producer which produces many events. It goes through our Redis driver, which writes the information to the Redis database and publishes the events using a publish-subscribe mechanism. And then we have containers. We have 130 containers on every server, which receives these events and in general acts upon them. And this first test just notes that the event was received. You note that the actual producer server also has a consumer. This is to be able to notice, to have a more accurate information about the timing, because synchronizing 33 servers is difficult. So the first test, we sent 10,000 events from the server. We send these events to 4,160 containers. So that number times 10,000, we get about 41.6 million messages that were sent in total. It took us almost a minute to have these events reach all the nodes. So we can see that we can reach, using this topology, about 177 events per second. So in theory, we can handle up to 177 API requests per second. So now we wanted to see how well we work with the entire system, not just the database. So we have a small scale setup. We have the same 39 servers. We have the same 6 Redis servers on the bottom. And we have 32 servers which act as one producer and many consumers. Once again, we send API events from the server, and we see how long it takes the consumers, the controllers, to receive this event and construct the policy so that everything is ready to go. Here we have run several tests, because several options. The first test is creating 50 subnets for a single big tenant, one user with many networks. So we have one network, one router, 50 subnets. On top of these 50 subnets, we have a DHCP port and a router port. Spread across our 32 servers, that means we have 1,600 messages. It took a total of 47 seconds. So we reached the point where we can create one subnet per second, which is reasonable. Once we have done that, we went ahead and created 50 ports, one port per subnet. Once again, we have 1,600 messages, and this took us only 16 seconds. This allowed us to create 3 ports per second. 3 ports per second where all the nodes received the information, constructed the policies. This also means that packets that have to travel from one host to another host can do so. Everything is set up, everything is ready to go. 3 ports per second is nice. It gives us, it's faster than the time it takes to set up a VM. It's comparable with the time it takes to set up a container. So this is good. And the more interesting part is trying to create now 250 ports, which is 5 ports per subnet. And then we realize that we have 8,000 messages, and it takes 82 seconds. And we see that we still reach 3 ports per second. So our performance is consistent, and it shows that with a relatively large number of ports, we can still have we still have reasonable performance, or very reasonable performance when it comes to creating ports. Now comes the more interesting bit. We wanted to see how to simulate a large-scale environment. Now, we don't actually have 4,000 servers, sadly. So we had to simulate that. We used containers to do this as well. We created on each server that we have created about 130 containers. Each container holds the Dragonfly controller. It also holds an OVS bridge, which is what we use to implement the network policy. And the test is the same test. We send API commands through the Dragonfly server, and we see how long it takes these API commands to take effect in all of the compute nodes, all of the hosts, or in this case, all of the containers. And we repeat the same tests. The first test is, again, creating 50 subnets, which includes one network, one router, a DHCP port per subnet, and a router port per subnet. Now that we have more than 4,000 nodes, this means that we have more than 200,000 messages that have to be propagated through the system, and it took 49 seconds. It's interesting to note that in the small scale, it took only 47 seconds. So we still can only make one subnet per second, but we see that this is almost unaffected by the fact that we have now 130 times 130 the number of hosts, which I think is amazing. So this shows that our system scales and scales well. We repeat the second test. The second test is creating 50 ports, one port per subnet. And again, we have 200,000 messages that propagate through the system, and it takes 17 seconds, which is only 1 second more than what we had in the small scale. And we have about 3 ports per second across 4,000 simulated compute nodes. So it still scales. I still think this is amazing results. And the third test is creating 250 ports, 5 ports per subnet. This means we had to send about 1 million messages through the system. That means that we use the Redis database to send about 1 million messages to 4,000 compute nodes, and we saw how long it takes the dust to settle with this in this environment. And again, it took about 86 seconds, which is about 5% more than what it took in the small scale. So we still have 3 ports per second. It is still faster than the time it takes to set up a VM. It is still comparable with the time it takes to set up a container. And it still scales, which is great. So this is the main conclusion. It scales. And now we can see some of the timing one next to side by side. We can see that the test running time is almost identical. We can see that the number of events per second we're able to send out is very, very similar. Now we have to remember that the first test that we ran with Redis only, we reached as much as 177 events per second, which is much more than our system can handle at the moment. And this was already with 4,000 nodes. So this means that while we are scalable, Dragonfly is scalable, there is still a lot of room for improvement. But what's very interesting is that Redis itself, what's very interesting today is that Redis itself proves itself as a very reliable backend, both as a database and as a publish-subscribe mechanism. We were able to use it to reach a scale of simulated 4,000 nodes. I think that's very nice. That's it.